All right, I've got a really brief, basic overview of types of reactions. Again, this will all help you with reviewing for your final exam because that's coming up. So this being our last unit, if you remember this, this will help you out. For our redox reactions, first of all, let's start with like the very, very basics. What is a reaction?
It's what creates a product.
Okay, yeah, creates a product. So in a reaction, something new is going to be formed. In any type of chemical reaction, you are going to start with your reactants. Typically, we show those on the left-hand side. So reactants first. If I can get this to work. So reactants first. And then how do we separate the reactants from the other side? An arrow. And what's on the other side? Products. It is only a chemical reaction when you actually create something new. So this is where the net ionic equation came into play in our previous unit. If you're not creating something new, so if I start with liquid water that is chemically H2O, and then I evaporate it and it turns into water as a gas, it is still chemically H2O. I did not create anything new. That is not a reaction. That is a physical phase change. All right, so a redox reaction, we defined those by saying a redox reaction has a single element somewhere in the reaction. So either on the reactant side or on the product side, please stop whispering. There's going to be a single element somewhere. And then of the types of reactions, or of the redox reactions, we had single replacement, combustion reactions, synthesis, and decomposition. Do you remember the difference between them all? All right, what is a single replacement reaction?
One compound plus one element, and that one element replaces one of the elements in that compound.
Good. Okay, so you have a single element and you have a compound, and this single element is going to come in and replace one of those. So let's say I called C positive. Oopsies. Okay. If I called C positive, if this is a metal, who is C going to replace? C is going to replace who? A, and then be bonded to B. So my new compound would be CB plus A is kicked out and now single. Good. Okay, so that's a single replacement reaction. So I'm going to say one replaces another. What about a combustion reaction? So you add oxygen. So if I have A plus oxygen gas, which is O2, not just O, but O2 specifically, what would it produce? Just AO, yeah. Depends on what it is. But like magnesium and oxygen, for example, if I had magnesium plus oxygen, it would just produce MgO because you have the +2 and the -2 charge. Perfect. So something combining with oxygen is going to be combustion. What about synthesis?
Is that when you like break it down?
No.
Synthesis means, I'm going to give a little description of this one. So we have O2 as a reactant. In a synthesis reaction, what is that? To create something. So in a synthesis reaction, we can tell that it's synthesis because why? Multiple reactants coming together to form one product. So in a synthesis reaction, just one product. So for example, if I had element A coming together with element B, and they formed compound AB, that would be a synthesis reaction. And then I always teach synthesis in conjunction with decomposition. Decomposition is what? Just the opposite, meaning? Perfect. Okay, so one reactant, and that would be like AB turning into A plus B. So AB breaking down into A plus B. So that was like a super quick overview of what we spent like 3 weeks learning. Then the other side of this, if you weren't a redox reaction, the other way we classified you was as double replacement. And then we had 2 types of double replacement reactions, and that is kind of where our last unit left off, was with precipitate reactions. So precipitate reaction is a type of double replacement reaction. Remember that with a double replacement, you're going to have, where's brown? Compound AB plus compound CD reacting together, and every double replacement reaction is going to follow the same pattern of the outside ones go together and the inside ones go together because they're switching partners. So your cation here will bond with your anion here, and your cation from the second compound will bond with your anion from the first compound. So visually, that's how I typically look at it, and it would be written in that order. So AD plus CB, or you can call it CB plus AD. Does not matter as long as you have them paired correctly within the compound. So if I were to actually assign something to this, if I'm doing a precipitate reaction, and I say, okay, I'm going to do lead acetate, so PB, and then C2H3O2 with a 2 on the outside. That 2 tells me that my lead has a +2 charge. Then I would add to that my next compound, which is going to be HCl. What would I call HCl? Hydrochloric acid. So this is an acid. Does that make this an acid-base reaction? If there's an acid reacting, is it automatically acid-base? I feel like a dead giveaway should be the section that it's in. Is it in the acid-base reaction section?
Yeah.
No.
It's not.
Yeah.
Goofball. All right.
It's not.
It's not. Okay. So this is an acid, but it's not an acid-base reaction. So we're going to review why we call something an acid-base reaction later. If I have this reaction following the same format that we just outlined in brown up there, my lead is going to bond to chlorine, and my hydrogen is going to bond to acetate. But when we're forming new compounds, we need to crisscross their oxidation numbers so that we have the correct subscripts. So lead has a +2 charge. Again, I can tell because of the 2 on the outside of the parentheses for acetate. And then chlorine has a -1 charge. So this would be called PbCl2 plus, and then hydrogen would bond to acetate, so it would be HC2H3O2. So I would call this lead 2 chloride, and this would be acetic acid. If I were to balance this, I would start with the things that are super simple to look at. So over here, I see I have 2 chlorines. I would need 2 chlorines over here, so I'm going to go ahead and put a coefficient of 2. 2 in front of HCl, 2 times 1 hydrogen. I would need 2 hydrogens over here, so I'll put a 2. 2 times 1 hydrogen, good. 2 acetates, good. And then everyone is balanced. So typically with our double replacement reactions, because we've already taken into account their oxidation numbers, they're super easy to balance.
You always have to balance them.
Yes? And then to determine if something is an actual precipitate reaction, you need to look at, was a precipitate formed? And we just got through the solubility unit where we were using our solubility chart. So I would look up my products on my solubility chart. This is how soluble something is in water. So if I'm looking at this one, my products are PbCl2 and HC2H3O2. So first of all, if I look up acetate, acetate is in the soluble section, and there are no exceptions. So is my acetic acid going to be soluble or insoluble?
Soluble.
What state of matter would I call that? Aqueous. So next to this one, I would put a little AQ. PbCl2, however, if I go down here, Cl is right here. It is also in the soluble section. However, there are some exceptions to that. Compounds of silver and lead and mercury. Is my chlorine in this example bonded to any of the exceptions?
Yes.
Yes, it's bonded to lead with a +2 charge, which means that this is going to be insoluble. So what would I write next to it? S for solid. Good. If I asked you to circle the precipitate, what compound would be your precipitate? PbCl2 is my precipitate in this case. Perfect. Because a precipitate is formed, that makes this a precipitate reaction. So we have spent quite a bit of time on that. And then now we're going to finally hone in on acid-base reactions. These are also called neutralization reactions. This is a double replacement reaction, so it's going to follow this same format that we did up here, the AB plus CD, where your acid, H bonded to something, that's element X, like a variable, plus Y, like another variable bonded to OH, which is a base, produces a salt and water. So I'm going to copy down AB plus CD produces AD plus CB, just so that you see that again. Again, the way that I think of it is that your outside ones go together and your inside ones go together. If that doesn't help you, what's really happening is that your cations and anions are trading partners. So as long as everyone on the product side gets a new partner, you're good, and you just put it in that order. So if I give you an example of this one, I'll do pinkish. I'm going to start with HCl. So this is my acid plus my base, which will be NaOH. That's that. Then what's going to happen is my outside things will go together. So my hydrogen will go with my hydroxide, and then my inside things will go together. My sodium will go with my chlorine. When I rewrite them on my product side, I need to make sure that I'm crisscrossing them with the appropriate oxidation numbers, therefore the right subscripts. That way everyone is nice and neutral. In this case, it's super easy because hydrogen has a +1 charge, chlorine has a -1 charge, sodium is +1, hydroxide is -1, so everyone's got ones all the way around. So my new products would be what and what? HOH.
NaCl.
Perfect. So this is my acid-base reaction where it produces a salt and water. Remember that salt does not just mean NaCl. So NaCl, that's sodium chloride, that's the kind of table salt that we eat. So typically when we're talking about salt, that's like daily life salt. But in chemistry class specifically, we are defining salt as any ionic compound. So in this case, it just happens to be NaCl, but it could be any ionic compound. And then to go back to the question that Gabriel was asking earlier about why we write it as HOH, this is usually why. So if you don't like seeing HOH, you can write it as H2O. That's totally fine. You just have to be able to recognize that this is water. So we got HOH because we bonded our positive hydrogen to our negative hydroxide. And that one's already balanced. Do I need to look for a precipitate in this?
No, it's because it formed the salt.
No, because it's going to form the salt, it's going to form the ionic compound, and water. If you wanted to, you could, but every time it would be soluble. You will not have an acid-base reaction that also produces a precipitate in the same reaction. Yeah.
How do you tell if something's a precipitate?
By looking it up in the solubility chart. So soluble means that it's going to form an aqueous solution, and insoluble means that it's going to form a solid, which is your precipitate. If it's anything in this section, it would generally form a precipitate unless it's bonded to an exception, then it does the opposite. Same thing with up here. Generally, these are going to be soluble, form an aqueous solution, unless it's bonded to an exception, then it's going to do the opposite. Okay. You can quiet the voices in your head. It's okay. Got it. Alright, last little bit we're going to get through and then we are done for the day, is neutralization. So a neutralization reaction is just another way that we say acid-base reaction. The reason for this is that in order to neutralize an acid, you add a base, and in order to neutralize a base, you add an acid. So neutralization reaction is a reaction in which a strong acid and a strong base react in aqueous solution to produce a salt and water, which is the same thing we've been saying this whole time. The resulting solution is going to be neutral. So when we say neutral, I mean not acidic and not basic. And then just as a reminder of exactly what we wrote up at the top, a salt is going to be an ionic compound made up of a cation, which is typically a metal. Not always, it could be a polyatomic ion. Anything that has a positive charge. So a cation from a base, and an anion from an acid. So that would be your nonmetal. It says A-N-I-O-N.
So it's not that.
What?
So it's not.
That's not gonna call.
I can send the recording to your mom.
That's fine.
Okay. So our example here is if I have the reaction between hydrochloric acid and calcium hydroxide, it is going to neutralize both my acid and my base. So hydrochloric acid reacting with calcium hydroxide is still a double replacement reaction like it was before, where my outside things get together and my inside things get together. Hydrogen would bond to who? Hydroxide, which we would just write as HOH. This 2 does not come with it because the 2 came from calcium. So when calcium with a +2 charge and hydroxide with a -1, sorry, I had it right the first time, -1 charge, when they break up and get with new partners, calcium gets its 2 back. And then I end up with CaCl2. If we balance this one, so if I'm looking at this, getting rid of all the extra stuff, to balance it, I have 2 chlorines on my product side. I have just 1 chlorine on my reactant side, so I need a coefficient of 2. 2 times 1 hydrogen. I'm going to want another hydrogen over here. And then I've got 2 of everything except for calcium's got 1 on each side, and we're good. If you still need an R and P chart to balance, you can absolutely do that, yes.
Can you also write H2O as H2O?
Yes. If you prefer seeing it as H2O, that is fine. It just generally makes it a little tougher to balance. But yeah, as long as you recognize it both ways, that's fine. So, from what I just said, you can neutralize an acid by doing what?
By adding base.
Adding a base. Good. Or you can dilute it by adding water. So water will act as both an acid and a base. So in this case, if I'm trying to neutralize an acid and I add water to it, the water will act as a base. This is where it comes into play that water breaks up into both hydronium and hydroxide ions. So water will act as a base in neutralizing an acid. The other thing that's happening here is you're diluting it. Which makes it less strong and easier to neutralize. And then you can neutralize a base by doing what?
By adding an acid.
Excellent. And by adding an acid, you can also do what, do you think, if you had to guess?
Adding water.
Add water, and how is water going to act in this case?
As an acid.
Good. So that would also dilute it. Same thing. And we will end with these 3 practice problems on predicting the products of acid-base reactions. So this is something that we have been doing pretty consistently since our reactions unit, so hopefully you haven't forgotten all of your skills. In the blanks, we're going to write in an acid-base reaction, one of the products is a salt, and the other is water. If it feels like we've written that 10,000 times, it's because we're getting close. Since salts are what type of compound? You will need to crisscross their charges to determine the chemical formula of the compound. So I'm going to pause here, give you a chance to write this out, and then I will check in with you in like 3 minutes to make sure we've got all the right answers. So predict the products of each of the reactions for A, B, and C. All right, so hopefully you were able to work through them. Make sure, hold on. Make sure that you have parentheses around your OH. Anytime you have a subscript on it, you have to have parentheses. Make sure that you're able to balance it. If you have questions on any of these, you can come see me. Otherwise, that is it.